Hello everyone and welcome back. My name is Mr. Koval, and in this video I'm going to show you how to do the titration of a weak acid with a strong base. And so I'm going to show you how to do the titration curve and how to graph that as well and what it looks like. And so let's get into this. So in my previous videos, I showed you the titration of a strong acid with a strong base. And in this video, we're going to look at a weak acid being titrated with a strong base. And we saw before with the strong acid is that we saw an S curve. And so we're going to see what kind of curve we get here. So let's get into this. So the steps that are the same. So we're going to calculate the volume of the NaOH we need in order to reach the equivalence point. So since they're giving us 25 milliliters of a weak acid this time of this concentration, what we want to do is calculate the number of moles of the acid we have. Because at the equivalence point, the number of moles of the NaOH that we add should equal the number of moles of the acid that we began with, so that they neutralize out and we have zero of the acid left. So we've completely neutralized our acid. So we need to figure out the number of moles of the acid. So we're going to take the volume and the molarity, and we're going to use that to find the moles. So since we have the molarity, we're going to use that as a conversion factor. So we're going to convert this to liters. So we have 0.025 liters, and we're going to put that over 1, and we're going to use the molarity as a conversion factor. So 0.100 molar is 0.100 moles of the acid over 1 liter of the acid. So liters cancels out. You multiply 0.025 by 0.100, and you get 0.0025 moles of your acid HCHO2. So this is the number of moles that we have in our Erlenmeyer flask that needs to be neutralized by the strong base. So now that we know the number of moles, this is going to be the same number of moles of base that we need to add in order to neutralize this number of moles of the acid. So now that we have that, all we need to do is use the molarity of our base, and we're going to find the number of milliliters or liters. So here, we just take the same number, 0.0025 moles, and this time it's going to be NaOH. Since this is the number of moles we have to add to neutralize the same number of moles of hydrogen, and we're going to use our molarity as a conversion factor. So then we multiply this. Again, 0.100 moles is 0.1, or molar is 0.100 moles per liter. So molarity is moles per liter. So we have on the moles on top, so we're going to have to put 0.100 moles on the bottom, 1 liter on top. So this time moles of the NaOH cancel out, and we're left with liters. And if we multiply that, we divide 0.100, we're going to get 0.025 liters, which is again equal to 25 milliliters. So that is the volume that we need. So 25 milliliters of the strong base is what we need to neutralize the 25 milliliters of our weak acid. And so if you remember from my previous video, I got the exact same value, number of milliliters, when we had a strong acid with a weak, so a strong acid with a strong base. Everything is exactly the same as that problem. The only difference is that we are we have a weak acid instead of a strong acid. But when we do the calculation, the number of milliliters of the base we need to neutralize the weak acid is the same as the number of milliliters we need to of the base to neutralize the strong acid. So the amount of volume you need does not depend on whether it's a weak acid or a strong acid. What it depends on is the the volume and molarity of the acid. So this will get you the number of moles. So it depends on the amount of acid you have, the number of moles of acid you have to titrate, and the concentration of the base you're using to titrate the acid. Okay, so those are the only two things you need that are going to affect the amount of volume you need. So keep that in mind. So now that we have this volume, 25 milliliters, let's move on to the titration part. So this tells us like the amount of volume we need to titrate and reach to the equivalence point. So what about at the 5 milliliter mark? So if I erase this, so we know that 25 milliliters is going to be at the equivalent. So I have 25 milliliters here, so that's going to be at the equivalence. So now we can start doing our pH calculations at various points of our titration. So initial pH before anything is added. How do we calculate the initial pH? Well, in the strong acid problem, the way you calculate the pH from the initial concentration of your acid was because it was from the concentration of the acid itself, because the strong acid ionizes completely in water. So whatever concentration of the strong acid you have, that's going to be equal to the concentration of H plus ions you have. And so all you need to do is take the concentration of your acid, take the negative log of that, and you've got the pH. In a weak acid titration, where you have a weak acid being titrated with a strong base, it's not that simple. So before you add any of the base to your solution, you have a weak acid problem here. So this is a weak acid, so it's in equilibrium, and so you need to do an equilibrium problem. So you're going to have to set up an ice chart. So let's set up our ice chart. So we need the equation. So the equation that we are dealing with is going to be our acid. So we have HCHO2 aqueous, and that's going to be reacting with H2O, and so that's going to give rise to H3O plus aqueous plus the leftover carbonic conjugate base, so plus CHO2 minus aqueous. Okay, so here's our equation for the weak acid, and this is an equilibrium problem. So we need to use our ice table. So here we have our ice table here, and so we start off with a concentration of this. So here we can convert. We need to know the concentration. So we have 0.100 of this. So we have 0.100, and we're going to ignore water, so we don't need to worry about water. And our H plus concentration, this is effectively 0 at this point, 0.00. So we don't need to worry about that. And then this is also going to be 0, because in the initial we're assuming everything stays together. So again, this is going to be 0.00. And the one thing I want to point out again, just to remind ourselves that when we're doing the ice table for an equilibrium problem, for something in equilibrium, we're using concentrations, not moles. So that's really important to remember. So when we're doing stoichiometry problems, we're using moles in our table. If we're doing an equilibrium problem and we're using an ice table, then we're using concentrations. So 0 concentration for these two and 0.100 concentration for the weak acid. And then we do our change. And so since we got 0 on this side, the equation is going to go towards the products. So that means we're going to lose some of our reactant, our acid. So we're going to have a minus X there. Everything is 1 to 1. So this is going to be a plus X. So we're going to gain some of our H plus, and we're going to gain some of our conjugate base here. And so when we add this together, the equilibrium expressions are going to be 0.100 minus X, and then we have X and X. And so now we have our ice table set up. So we just need to get our Ka value for this acid. And the Ka value is, pardon me, 1.8 times 10 to the negative 4. So the Ka is equal to 1.8 times 10 to the negative 4. And our Ka expression is Ka is equal to the concentration of these two, right? So the concentration of CHO2 minus multiplied by H3O plus all over the concentration of our acid. So that's the concentration of HCHO2. And so all we need to do is put in the equilibrium expressions. We can try the X is small approximation and see what we get. And so we'll do that. So we plug in these values. So we plug in X and X, so that's X squared. So X squared over, and then we have 0.100, so 0.100 minus X is going to be equal to 1.8. So 1.8 times 10 to the negative 4. And so at this point, you can do a few things. You can either use your quadratic formula to solve for X. You could use the X is too small. Try the X is small approximation. If it's valid, then you can use that X value here for the H plus concentration. If not, then you could use the quadratic formula, or you could use the method of successive approximations. I've covered that in other videos, so you could go see those in another video if you look that up. So at this point, you can find X pretty easily by the X is small, and I did that already. So X is going to be equal to 4.24 times 10 to the negative 3. So X ends up being equal to, let me say that again, 4.24. So 4.24 times 10 to the negative 4. And so what that means is that that is equal to X here, which is your H plus concentration. And so all you need to do now is then use the pH is equal to the negative log of the H plus concentration. So all you would need to do is you have pH that's equal to the negative log of your H plus concentration, which is this right here, 4.24 times 10 to the negative 4. And so you do that on your calculator and you get 2.37. So the pH is equal to 2.37 to begin with. So that I can mark on my graph here. So 2.37. So here I have 2, so 2.37 is at 0 is going to be, let's see, that's 3. 2.37 might be around there. So this is the initial pH. This is the first point on my graph. And so that's how you find the initial pH of a weak acid solution or a weak acid before you've added any strong base. So basically it's a weak acid problem, just like we've done before. Okay, so now what about the pH after adding 5 milliliters of NaOH? So the first thing we want to do is we want to set up a stoichiometry table because we're adding a strong base, and the strong base is going to react completely with the acid. So we got to get our table set up. So we're going to have a new reaction here. So we'll set up our table for a new reaction. And so we'll get rid of our numbers here. And we'll replace them. So give me a moment while I get this together. Okay, so the new equation, since we're reacting base, we're throwing in base, so we're going to need to have our OH minus concentration. So we have our OH minus concentration plus, and that's going to react with the acid, so that's HCHO2 aqueous, and that's going to produce the products, and the product is going to be the water. So water is one product, and then that's going to be liquid, and then plus we've got our conjugate base left over, so that's going to be CHO2 minus aqueous. So so there's our equation. So this is the reaction that's taking place when we add our base, our strong base. So what do we do now? Well, since we're adding a strong base, that strong base is going to react completely with the acid. So this is a stoichiometry problem. It's not an equilibrium problem. So we got to do our stoichiometry first. So remember, when you're dealing with a buffer situation, and which is what we have here. So when you add your strong base, originally we just had the acid with a little bit of our conjugate base, practically zero. But once we start adding the base to the acid, we are producing more of the conjugate base. And so now we're going to have some conjugate base in with the weak acid, and that's a buffer situation. So once you start adding base to your weak acid and you're trying to neutralize it in your titration, at that point you've got a buffer situation going on. So you got to treat it like a buffer situation. And so with buffers, remember, when you're dealing with the buffer situation, when you add stuff to a buffer, you're going to need to do a stoichiometry problem first and then do the equilibrium problem. So that would be an ice table or Henderson-Hasselbalch equation. I'm going to use the Henderson-Hasselbalch equation. Okay, so here then we got to set this up. So this is going to be before adding, this is going to be when we add, and this is going to be after adding. So we add 5 milliliters of NaOH. So we need to figure out the number of moles of NaOH that we add. So again, we're going to take the volume and we're going to take the molarity and we're going to calculate the number of moles. So we're going to convert this to liters. So we have 0.005 liters of our NaOH. we're going to take the molarity and we're going to multiply using that a conversion factor. So this is going to be 0.100 moles per 1 liter. Liters cancel out and you got moles. So here we've added 0.0005 moles of our NaOH. So that's the number of moles that we added. So let's add that to our table. So what do we have before we add? So we have practically zero. So practically 0.00 moles of our OH minus. The only OH minus we have here is from the autoionization of water, which is very, very small. We have we have 0.100 molarity of that. So again, the number of moles, we calculate the number of moles, we're going to take the volume in liters, so that's going to be 0.025 multiplied by 0.1 gives us 0.0025 moles of our acid. And again, when we're doing our ICF table or doing our stoichiometry table, everything is in moles, not molarity. Water, we are going to ignore. We don't need to worry about water. And then for this, before anything is added, this is practically zero. So this is pretty much 0 moles. So now that we know how much of the base we're adding, how much hydroxide ion we're adding, that's this many moles, we're going to put that in this right here. So we've got 0.0005 moles. So that's the amount of base we're adding. So this, we're not adding anything to that. We're not adding anything to this. So because the base is going to completely react with the acid, at the end, after we add it, it's going to react completely and go away. It's going to be practically zero again. So now we're back to practically zero. So 0 moles. So then what that means is that we lost 0.0005 moles here. If we lost it here and this reacts with the acid, then we also lost it here, right? So that's going to be a minus 0.0005 moles. And if we lost it here, since this is a 1-to-1 stoichiometric ratio here, 1-to-1 mole ratio, then whatever stoichiometric amount we lose here, we gain it here. So that's going to be a plus 0.0005 moles here. And so now we can figure out, we subtract this from this, and we get 0.0020 moles of our acid left, and we gained 0.00505 moles of our conjugate base. So now we have conjugate base with our conjugate acid. We've got a buffer situation here. So now we can do the Henderson-Hasselbalch equation for the equilibrium portion of the problem. So remember, when you got a buffer, there's two parts when you're adding something to a buffer. So you've got the stoichiometry part, which we did, and then you've got the equilibrium part, which is what we're going to do with the Henderson-Hasselbalch equation. Or if you like, you can do an ice table and do it that way as well. Okay, but before we go on to the Henderson-Hasselbalch equation, you have to revert everything back to concentrations. So you can't stick moles, but actually you can stick moles. Why can you stick moles? Is because the volume, whatever the volume is going to be, it's going to cancel out anyway. So you're going to be left with moles in the end. So using the moles, you can stick that into your Henderson-Hasselbalch equation. So the Henderson-Hasselbalch equation, again, is pH is equal to the pKa plus the log of the base over the concentration of the acid. Sorry about it, the lights went out again. So at this point, we can now use the moles, plug the moles in, and calculate the pH at 5 milliliters. So let me see what the pKa is. The pKa of our substance is 3.74. So the pKa, so pH is equal to pKa, which is 3.74, plus the log of the base, which is going to be 0.0005, divided by the acid, which is 0.0020. And then when we calculate that out, then the pH becomes, I already calculated this out, it's going to be 3.14. So now the pH is 3.14 after adding 5 milliliters of your NaOH. And so here we can add this point to our graph. So at this point here, 5 milliliters, we get 3.14. So 3 is about there. So 3.14 is going to be maybe about there, I guess. Close enough. Okay, so there is our 5 milliliter pH. Okay, so what about these other points? So now what about at 10, 12.5, 15, and 20? Well, at these points, the process is exactly the same. So at 10, you would then figure out the number of moles of your base added. So you have 10 milliliters of your NaOH. Use the molarity to find the number of moles. Then you would do a stoichiometry table. So you would have the OH minus, you do your stoichiometry table. You'd have, this would be the same, your before adding, this is before adding, this would be exactly the same. This would be different because you are calculating a different number of moles of your OH minus because you're adding more base. So this would be different. And so your concentration or your number of moles of H, your acid, would go down, and then this would go up. And so once you figure those out, you just plug those into your Henderson-Hasselbalch equation, and it'll spit out the pH. So you can do that for each of these volumes. I did that, and so I have the pHs here. And so for 10, it is 3.56. So 3.56 is the pH for 10 milliliters. For 12.5 is 3.74. 3.74. For the 15, it is 3.92. And for the 20 milliliters, it is 4.34. So 4.34. So these are the pHs at each of these volumes, doing the exact same thing I did here. I'm not going to spend the time to do it here. So, but if you understood the 5 milliliter, then you do the exact same thing for these as well. So this is before you get to the equivalence point.